watch this part 2 video until you've watched part 1. This is part 2. Do not watch it until you've seen part 1. Okay, in our last video we spent time talking about electron addresses. Where do they hang out? We talked about principal energy levels. We looked at sublevels and the orbitals that exist inside those sublevels, like S, P, D, F, G, H, I. Woo! And then we talked about how they're spatially arranged in 3D space. And then we talked about the electrons, how they spin opposite of each other. And we talked about the idea, guys, that Pauli said you can't have two electrons occupy the exact same address at the same time. And that the most number of electrons you can have in one orbital, think 2p in the x direction, is 2, and they must spin opposite of each other. So then we talked about the shapes of orbitals. We looked at very briefly the S sublevel, the P sublevel. We looked at the D sublevel and the F sublevel. Okay, let's move on. So we look at the energy levels and occupied sublevels. And those are our basic energy levels here and the sublevels that can be occupied. Now, the truth of the matter is, when you get to the higher levels here, like 5, 6, and 7, you have other levels that exist because electrons can jump to a higher state. But at this point, we're not concerned about that. We're only going to go S, P, D, and F, and that's it. Period. End of story. So with that, we talked about the idea that principal energy levels, the higher the energy level you go, the bigger it gets. Why? Well, because you're further away from the nucleus. That's why. That's the idea. So here's 1s. Here is 2s. Okay, this is like a computer-generated pictures. Here's 3s. So you kind of notice they get big. And here's 2 in the 2p. Okay, and you say, well, what's up with the dark line there? Well, part of the thing about that dark line is just the area where you really don't find electrons. That's just it. So we said that there's an order. There's an order in which electrons fill the levels and sublevels in each atom. So you start out, fill out 1s, then 2s, then 2p and 3s, then 3p, oh, whoa, you got 4s before you fill 3d. Wait, what's up with that? It has to do with the idea of low energy level, but we'll get to it in a moment. So if we look at the periodic table, it is organized by the electron configuration of our elements. Okay, so when we go down a column, okay, when we go down a group, you notice each time you add another level there. When you're going across, again, you're adding more electrons to the thing. And remember, from 4s to 4p, you fill 3d first. That's how it works. And the thing about it is, as I said here, consistency. This is all true for those atoms there. Okay, let's move on here. So we got to talk about atoms. Atoms can either have a positive charge, a negative charge, or they can be neutral. Now some people would say, well, what difference does that make? Well, if atoms aren't positive or negative, we're not going to get chemical reactions happening, and life as we know it just would not be possible. If all atoms were totally neutral, things aren't going to go together very well. So that means that atoms have to have some kind of a positive or negative charge. But in neutral atoms, electrons and protons are equal in number. In other words, the positive of the electron, the positive of the proton, the negative of the electron separate from each other. In other words, they're opposites, they cancel each other out. So our periodic table is arranged by atomic number. The atomic number is the number of protons in the nucleus of the atom. Now some people would say, what difference does this make? You know, how is this going to help some hip-hop star's career? It doesn't. But the idea is that the atomic number tells us what the atom is going to be, much like the DNA tells us what we're physically going to be. You're going to be human. You're going to be male. You are going to have a certain skin color, hair or lack thereof, Okay, you have all those things there. So there's an identity thing there. We also got to talk about the Aufbau principle. So here's the idea. In Aufbau, hypothetically, electrons that orbit one or more atoms, they fill the lowest available energy levels before filling up the higher levels. Okay, that's just the way it is. You're going to go for the easiest thing to fill up first, which is why, ladies and gentlemen, we have a certain order where these electrons are filling. And that's why when we say from 3p, 4s is easier for the electrons to go, and then we go to 3d, then 4p. Then notice we don't go to 5p, we go to 5s, then we go to 4d. So there's a lot of things that are involved here in terms of filling the thing up. And I do give the parking garage, Jurassic Park parking garage at Universal, to give you guys a rough idea of what that would look like as an analogy. Okay? So that's the Aufbau principle. You're going to fill the lowest available energy orbital first. Now, we also have to look at electron configuration. We know electrons have addresses. Yay! Okay. But how are they arranged? How are they put in? So we're looking at how the electrons are arranged. Now there's 3 pieces of information we need. We don't worry about the spin here. Okay? Principal energy level, our sublevel, and the number of electrons. So for example, hydrogen. Let's take the simplest one. It's got 1 proton, 1 electron. Now we're not worried about how many protons it's got. It's got 1 electron. So hydrogen is going to be level 1, our basic energy level, sublevel S, our orbital, our s orbital, and there's only 1 electron to it. Now we can look at something like helium. Helium would be level 1, sublevel S, but helium has 2 electrons. They fit inside the s orbital in our sublevel, and it would look like this. That's what it would look like. But it is also true that we can write it like this. Okay? So we're saying this is a noble gas. What's up with the noble gases? They don't react that easily. You don't hear about helium balloons blowing up. You don't. Hydrogen? Yes! But helium, no. Now let's take a look at lithium. Lithium's got 3 electrons to it. So we got 1s2. So we're filling our rule here. The lowest available energy level is filled. Then we have 2s1. Or we can write it another way where we have the bracket with the He saying, hey, it's just like helium, and we have a 2s1. Both of these are correct. This one is trying to use shorthand. You'd say, but I don't see the shorthand here. You do when you see the bigger elements, the larger atoms. Then that's when it becomes a lot more practical for us to work with. Okay. And again, we'll spend a little time in class on that. So we also looked at electron configuration. We got 1s1. Now we're going to look at orbital notation. So here's helium, 1s2. So we got a 1s here, and then notice we got an arrow going up and an arrow going down. So each arrow represents 1 electron. Now you've got an arrow going up and an arrow going down. Think about they're going opposite of each other because the electrons must spin opposite of each other, like we talked about in part 1, which hopefully you did watch before you watched part 2. That's why I was making that big admonishment to go watch part 1, because if you didn't watch part 1, you're not going to completely understand part 2 here. Okay, we got to move on. Okay, Frederick Hund. Okay, Hund's rule. As electrons fill a sublevel, all orbitals receive 1 electron with the same spin before they begin to pair up. I like to call this the Monopoly rule. You remember the game Monopoly? Many of you have played it. The rules say, right, if you have 3 lots and you buy 3 houses, because now you have the monopoly, you can build houses on there. You cannot put 3 houses on one thing. You cannot do that. That's what the rules say, right? Well, so what does that mean? You have to put 1 house in each lot. Then you can go and put a second house. And that's what the Hund's rule says regarding electrons. When they fill in those orbitals, okay, they fit in where they are available. You have to spread them out evenly. That's why I call Hund's rule the monopoly rule, because it's a great way to describe what that is. Okay? So if we look here, this just gives us an idea of, for orbital notation. So here's 1s, here's 2s, 2p, 3s, 3p, and so forth. And if you want to look at it this way, this is the energy level from low to high. So we can look at it that way. And you can see why we would have to go and fill in, before 3D, we have to fill in the 4s. It's a little bit less energy needed. And electrons are going to take the easy way through. It's just like any students we assign work to, right? If we sit there and say, look, here's our rubric, our checklist for how to get an A. Are you going to go and follow that checklist and get that relatively easy way to the A, or are you going to make things much harder on yourself? No, you're not. You're smarter than that. You can do this. So that's the idea, that electrons, they are going to fill the lowest available sublevel orbital, okay? And when they do, here, if you got multiples like 2p, they're going to go 1, 2, 3, then 1, 2, 3. And we do work upon that more in class. And with that, ladies and gentlemen, I am going to stop here. And this is the end of part 2 of chapter 4b. All right. Oh, this was filmed before school ever started. I'm just saying.